last few. So I'm going to try to make them available and put them on the notebook underneath where we talk about these challenge problems. So you'll actually be able to go back and not only see the work, but actually hear my voice. That may take me through the weekend to get these last few up, but that's what we're going to try to do now. So just be aware that we're recording. All right, so let's go and look at the class notebook. Hopefully. And we're going to look at this. We want to draw the Lewis structure for CF4. And then once we have that correct Lewis structure, we're going to then interpret the molecular shape, the bond angles, and indicate whether it's polar or nonpolar. Right? And in doing that, we're also going to record any of these non-zero formal charges. So we're going to go through the steps just like we did before. We're going to do these probably in a different order. So the first thing we're going to look at is the number of valence electrons. What's the total number of valence electrons we have in this molecule? Somebody. How many valence electrons do we have here? Anybody?
Would it be 34?
34. So we have each one of the fluorines has 7, and we have 4 of those. So 7 times 4 is 28, right? No, yeah, 28. And then we have the sulfur, which has 6. So 28 plus 6 is 34 electrons. Right? So if we do that, which one of these is the least electronegative, sulfur or fluorine?
Sulfur.
Right? Fluorine's the most electronegative, so we are going to put sulfur in the middle, and around that we are going to surround it with these 4 fluorines. And I'm going to do it sort of symmetrically because it makes everybody feel better, right? And then we're going to give, according to the steps, we are going to give everybody an octet. So if we have, look at that now, sulfur, because it's sharing 4 pairs of electrons, it has 8. Each one of the fluorines have 8. So how many total electrons are we showing in this structure? So we have each one is the same. So around this fluorine, we have 8. So 8 times 4 is 32, right? So we're showing 32 electrons in this case. We need 2 more because we have 34. So those last electrons go where?
On the sulfur.
On the sulfur. Any extra electrons that we have to go on the central atom. Okay. So now if we look around this central atom, right, our shape is going to be determined by the central atom. So we're going to look at what's going on right here around this central atom. Right. We have number of atoms around that. So we have 4 atoms around it. We have one lone pair. So if we use the book's notation, we have the central atom A, we have 4 bonded atoms, and then we have one lone pair. That's not what they use. They use X and E, right? Is that the notation that they use in the book? I always forget.
Yeah.
Okay. Right. So that means around this central atom, we have to put 5 places where we have electrons, right? These two numbers together equal 5. So there's 5 areas where we need to stick electron density around the central atom. So in this molecule, the electron geometry has to take into account those 5 places. So when we put 5 things around a nucleus, those electrons are going to spread out as much as they can. And what shape do we get when we have 5 areas of electrons around the central atom? What is our electron geometry?
A trigonal pyramidal.
So it's going to be trigonal. That's not misspelled correctly. Bipyramidal. Right? So if we look at what that shape looks like, maybe if I can draw. Right? If we look at this in terms of electrons, we have, in our case, we're going to put, we have a pair of electrons here, a pair of electrons here, a pair of electrons here, and a pair of electrons there, and a pair of electrons there, right? And it's called trigonal bipyramidal because if we enclose this structure and make it solid, right, we ended up with a pyramid, a 3-sided pyramid. That's where the trigonal comes from. But the pyramids go both up and down, right? So it's 2 pyramids on top of each other, so the trigonal bipyramidal. Okay. So let's put this back over here. And it's this placement of electrons that's going to dictate the overall bond angles that exist here, right? So it's these electrons that's going to dictate the shape, but also the bond angles, which is why when I always do it, you'll see me identify this electron geometry. Right? So if we look at this shape, and we back up from it. So if we're looking right now at the electrons, we see electrons here, 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 and here. If we back away, since electrons are really small, the places where we have atoms are still going to be present, but that place where it's only electrons is going to appear to disappear. Does that make sense? Because they're small, and you back away, only the large things, and if we can talk about atoms being large, are going to be visible. Which means that this lone pair has one of 2 possibilities of where it can exist. It can exist in this location, this top or bottom location, or one of these locations around what we call the skirt. Which one is it going to be? Where is that lone pair going to prefer to go? Is it position, what I'm calling 1 here, or position 2? Anybody want to guess? If you think, let's not, you don't have to, if you think it's position 1, go ahead and raise your hand. Good. If you think it's position 2, raise your hand. All right, so it is position. These electrons want to get as much space as possible. And when we put here, because of this, the angle between these two, actually, let's change the color. This bond angle here is 120 degrees. This bond angle between the top and that skirt is 90 degrees, right? So it actually has more room in this position too, right? Which means that when we back up, our molecule is going to look like this, right? Which is easier to see if we let it fall over and draw it correctly. Right? If we draw it like this, where that lone pair of electrons is sitting up here, that looks like a what is that shape?
Seesaw.
Right? If you look at it, it looks like it is a seesaw, and that's what I'm going to call it. If you want to be fancy, you can call it a distorted tetrahedral, right? That's what you'll find if you Google it, but that's no fun. So I call it seesaw because it's more fun to say and it's more fun to do, right? You can imagine the seesaw going up and down. All right, so if we go back up to the problem, we're supposed to give the molecular geometry, which is seesaw, the bond angles. Well, the bond angles for the electrons started out at 90 and 120. But because one of those is a lone pair, the lone pair is going to take up more space. And I always think of the electrons as I used to have a pug who we made the mistake of letting in sleep in bed with us. Right? So I had this little pug who was probably 14 inches long, but when they got into bed with us, it would take up seriously 3 feet of room, right? Which means that I ended up falling out of bed every day, right? Because between my wife and the pug, there was no room left for me, right? Because even though it's small, it's going to take up a lot of room. Same thing is going to happen here in this structure. This pair of electrons that we have over here is going to push everything else away, which means those bond angles, which started at 90, are now going to be less than 90 and less than 120. Right? We can estimate what that is based on the number of lone pairs and where it starts, but that's a lot of work. So we just need to know that it becomes less than. Does that make sense? So anytime there's a lone pair, we're going to take whatever our base bond angles were and just throw in the less than symbol. Questions on that?
So that's all you want when you ask for the bond angle?
Yes. If it's got a lone pair, you just put in whatever the bond angles were for this electron geometry, and then throw in the less than symbol in front of it.
Okay.
If there's no lone pairs, then it just stays as what it was. Oop, let me erase this. Okay. Any questions about what we've done there? Okay. All right. So the last thing that it asks, the problem wants to know is if this molecule is polar or not. Right? So if we go back to this shape, right, and I'm actually going to make it not going to draw it more of like, because it's less than 100 or 90, so this is going to be slightly bent. Right? If we look at the difference in electronegativities between these atoms, right? In the middle, we have this sulfur, and over here we have the fluorines, right? In our difference, which we already said, which is the more electronegative, is the fluorine, right? So if we go back to this idea that the electrons are going to move towards the more electronegative, and we can show that movement with arrows, right? We're going to see an arrow in that direction, an arrow in this direction, an arrow in that direction, and an arrow in this direction, right? Which means that all of these arrows are going to sum up So overall, we get electrons moving from the top of the molecule in the way it's drawn here towards the bottom, right? So the top of this molecule is going to be partially positive, and the bottom of the molecule is going to be partially negative, right? Or this molecule is going to have a dipole moment, which means this is going to end up being a, can't write words with an eraser, polar molecule. And since in all the problems that you're going to do today, I have you enter in yes or no. When asked about polar, it's going to be yes, it's polar. Okay. Any questions about that before we go back to the regular? The one thing that I didn't do, well, I did it, I just didn't do it for you, is if we look at the formal charges. Right? If we look at the formal charges in this molecule, because fluorine has 7 valence electrons, there's 6 lone pairs, so 7 minus 6 minus 1/2 of the shared, which is 2, that equals 0. Right? The sulfur has 6 minus 2 minus 1/2 of 8, which is also 0. So there was, I did it in my head, but there are no non-zero formal charges, so we don't have to show any. Questions? Comments? So is that somebody raising their hand with his question, or is that still held over from before? Any questions before we move into our groups to start working on today's activity? All right, a couple of things that I want to mention about entering stuff. When it asks for the molecular geometry or the molecular shape, I want you to put in the molecular shape without capitalizing anything and or using hyphens. I saw some people in the ticket to class hyphenated, like trigonal bipyramidal. So when you put it in there, it would just be under there as trigonal bipyramidal, no capitals. We're going to separate the bond angles with the and symbol, and make sure you include the degree sign. And then if it, in the questions where it asks if it's polar or not, you answer yes or no. Again, not capitalized, just the word yes or the word no without any capitalization, punctuation, or additional words. Questions, comments, concerns? All righty.